In any wireless network, the airwaves are a shared resource. If every device attempted to transmit data at the exact same moment, the resulting collisions would turn the communication into complete chaos. To prevent this, the medium access control sublayer acts as the intelligence of the system, organizing exactly how different devices share the medium. It provides the structured rules that allow stations to either compete for access or be granted permissions to speak. Coordination is built upon several sophisticated functional components, each designed for a different type of network demand. At the most fundamental level, we have the distributed coordination function. This is a contention-based approach where devices essentially listen to the medium and compete for the right to transmit. It is the baseline method for the basic communication. However, not all data is created equal. A video call requires different timing than a background email sync. To handle this, we use the hybrid coordination function, which introduces more sophisticated management through two distinct paths. One path is contention based, which we already discussed. The other path is controlled access, which provides even more precise management by assigning specific parameters to ensure a guaranteed level of performance. Beyond these standard interactions, the architecture extends to more complex environments. For networks where devices form a web of interconnected nodes rather than connecting to a central point, we use mesh coordination function to manage those distributed links. Finally, to further streamline how devices send data back to a central point, we use triggered uplink access. This allows the network to organize and facilitate transmissions from multiple devices in a highly structured way, reducing interference and ensuring the entire system remains efficient and orderly. In a busy wireless environment, not all data is created equal. If a device tries to send a massive file download at the exact same time it is trying to stream a live video call, the video call will stutter and drop frames. To prevent this, the network uses a system called Enhanced Distributed Channel Access to prioritize time-sensitive traffic over background data. Instead of treating every packet the same, the system organizes data into different access categories. Think of these as separate priority lanes on a highway. High priority traffic, like voice or video, gets its own queue with faster access to medium, while low priority data, like an email sync, sits in a different queue that waits longer for its turn. To manage how these queues compete for airtime, the device uses a back-off procedure. A station doesn't just transmit whenever it wants. It waits for specific triggers to start its own countdown. One trigger is when a request arrives that fills an empty high priority queue while the medium is already busy. Another trigger happens when a device finishes its current transmission opportunity, allowing it to check if it can send more. Crucially, an internal collision can also trigger a backoff. This happens if two different priority queues within the same device try to access the medium at the exact same time. In that moment, the higher priority category wins, and the lower priority one must restart its process. Before any transmission can actually begin, the device constantly monitors the environment. It uses physical and virtual carrier sensing to check if the airwaves are clear. It also tracks specific timers to ensure no other device is currently scheduled to transmit, ensuring that high priority data moves through network with the speed and reliability it requires. When a device is ready to send a large burst of data, it doesn't just start transmitting. To prevent collisions and ensure the medium is clear, it often initiates a handshake known as request to send and clear to send. It's also known as RTS and CTS. This exchange acts like a reservation system, telling every other device in the vicinity to stay quiet while the transmission takes place. As part of this reservation, the device must agree on how much spectrum they're going to use. This is where bandwidth signaling comes in. Before the actual data flows, the sender uses the handshake to signal the intended channel width. This ensures that every station listening to the exchange understands exactly how much space is being occupied. When a sender uses specific transmission formats to initiate this request, it must include a target address for the signaling and ensure that the timing parameters for the channel bandwidth are consistent. If these parameters don't match, the reservation might fail or cause interference. The system manages this through two different approaches: static and dynamic bandwidth operation. In static mode, the channel width is fixed and predetermined. However, dynamic bandwidth operation allows for much more efficiency. In this mode, the sender explicitly indicates that it is capable of flexible bandwidth use. When the receiver responds with a clear to send message, it evaluates the environment. If the receiver finds that the necessary subchannels are idle, specifically the non-primary 20 MHz segments that aren't being punctured by other traffic, it can authorize a wider channel. This flexibility allows the network to optimize its capacity on the fly, carving out the widest possible path for the data based on the real-time state of the radio environment. In wireless communication, sending data one small packet at a time is inefficient. Every time a device sends a frame, it has to wrap that data in headers and wait for a clear channel, creating a lot of overhead that eats into your actual speed. To maximize throughput, the MAC layer uses a technique called frame aggregation, which bundles multiple smaller frames into a single, much larger transmission. This allows us to send more actual data while paying the overhead cost only once. There are two main ways to do this. First, there is A-MSDU, which takes multiple service data units and packs them into a single MAC frame. Second, there is A-MPDU, which takes multiple MAC frames and bundles them together into a single physical layer burst. While both methods reduce overhead, they are governed by specific limits to ensure the signal remains reliable. The maximum size these aggregates can reach is determined by exponent values found in the device capability information. These limits aren't fixed. They change depending on whether you're operating in the 2.4, 5, or 6 GHz band. And they also depend on the specific type of physical layer transmission being used. We also have to be careful when we are sending data to a group of devices at once. If a single transmission is meant for multiple recipients, the system has to be conservative. To make sure every device in that group can actually process the incoming data, the system looks at all the associated stations and uses the smaller exponent value among them. This ensures that no single device is overwhelmed by a frame that is too large for it to handle. Finally, to keep the sequence organized, we maintain strict spacing between the individual units within an aggregate using a calculated minimum distance that is based on the current physical data rate. When we transmit data over a wireless network, the most intuitive way to ensure everything arrived correctly would be to wait for a confirmation after every single frame. However, sending a separate acknowledgement for every individual piece of data creates massive overhead, wasting valuable airtime. To solve this, we use a much more efficient method called a block acknowledgement. Instead of acknowledging frames one by one, a device can confirm the receipt of an entire group of frames all at once. Before this process begins, the communicating devices, which could be individual stations or more complex multi-link devices, must first reach an agreement to manage these acknowledgement sessions. This agreement establishes a transmission window, which essentially acts as a limit on how many frames can be in-flight or sent out before the sender must stop and wait for a confirmation. The size of this window is not fixed. It scales based on capabilities of the devices involved. If you're connecting to extremely high throughput stations, the system can support a much larger window of up to 1024 frames, allowing for massive bursts of data. In contrast, when communicating with older devices that lack these advanced features, the window is much smaller, typically limited to 64 frames. Security is also integrated directly into this exchange. In environments that require high levels of protection, devices can establish protected block management agreements, provided that both the sides meet the necessary security capabilities. This ensures that not only is the data transfer efficient and scalable, but the confirmation process itself is secure against interference or spoofing. In a busy wireless environment, communication isn't always a straight line. Because signals can interfere or get lost, devices often retransmit to ensure it arrives safely. However, these retransmissions can lead to a problem where a receiver gets the exact same piece of information multiple times. If a system processes these duplicates, it can cause errors, wasting processing power, or corrupting the data stream. To prevent this, the network relies on a system of sequence numbers and specialized caches to ensure every piece of data is unique and processed only once. Every frame sent across the air carries specific identifiers, including a sequence number and a fragment number, along with the source and destination addresses. When a frame arrives, the receiver checks these identifiers against a duplicate detection cache. This cache acts like a short-term memory, keeping track of the frames it already has seen. If a new frame arrives with an identity that matches something already in the cache, the receiver recognizes it as a redundant copy and discards it immediately. To keep this organized, the system manages these identifiers using distinct number spaces depending on the type of traffic being handled. For example, high-quality data intended for a specific device uses a numbering space indexed by both device's address and its traffic identifier. This allows the system to track different streams of data separately without them getting mixed up. When we look at devices that operate across multiple links, they maintain even more specific spaces to keep management instructions separate from the actual data being sent. Privacy is also a key consideration. If a device is using MAC privacy features, it needs to make sure its communication patterns don't reveal its identity. To do this, the sequence number counters are randomized whenever the device's address changes. By resetting these counters using a modulo operator, the device can maintain reliability while ensuring that an observer cannot easily track a single device across multiple sessions. When a network device needs to send a control frame to a group of different stations at once, it faces a significant challenge. A control frame, such as a trigger frame or a multi-station acknowledgement, is essential for coordinating the entire group. If even one device misses this signal, the entire communication sequence can break down. To prevent this, the transmitting device must be extremely careful about how it encodes the data. It looks at the capabilities of every single recipient in the group and selects a modulation and coding scheme along with a specific number of spatial streams that is supported by every single station. It essentially chooses the lowest common denominator for that specific group to ensure that no station is left behind. However, a problem arises when we have a mix of modern high-speed devices and older legacy devices. A high-speed frame might be sent using advanced techniques that an older device simply cannot understand. To bridge this gap and maintain connectivity, the system uses a process called rate conversion. If a high-speed frame requires a response from a device that lacks support for those modern high rates, the system doesn't just fail. Instead, it uses a mapping process to translate the high-speed modulation into a more basic legacy reference rate. Think of this like a translation layer. The system maps the advance rate to a non-high throughput reference rate using a predefined lookup table. When the older device receives this instruction, it looks at its own available speeds and selects the highest possible rate that is still less than or equal to that reference rate. This ensures that the responding device can communicate back reliably using the speeds it was built to handle, keeping the entire network synchronized regardless of how much technology has evolved between the different stations. To keep a wireless network stable and efficient, the media access control layer enforces several physical and temporal rules that govern how and when devices communicate. One of the primary ways it maintains order is by placing strict limits on how long any single transmission can last. Every station has a maximum allowable duration for its data transfers. By bounding these transmission opportunities, the network prevents a single device from hogging the medium for too long, ensuring that airtime is distributed fairly and that other devices have frequent opportunities to access the channel. Beyond these basic duration limits, the network uses more sophisticated timing mechanisms to manage power consumption and access schedules. Instead of a device constantly monitoring the airwaves and wasting battery, it can negotiate specific windows of time to wake up and communicate. This is done through target wake-up time mechanism, where a device and an access point agree on exactly when a station will become active. A device can approach this in several ways. It might request a specific schedule that fits its needs, suggest a preferred timing that works best for its battery life, or even demand a strict timing window to ensure critical data is sent without delay. As we move into more complex environments where devices use multiple links simultaneously, we encounter new challenges involving how a device handles simultaneous transmission and reception. Some devices are limited by non-simultaneous transmission and reception constraints. This means that the device lacks the hardware isolation to transmit on one frequency while simultaneously receiving on another. For these devices, timing becomes even more critical. For example, if a device receives a request to transmit on one link, it may be prevented from receiving data on its paired link if another device in its group is currently using its transmission opportunity. Managing these overlapping constraints is essential to prevent interference and ensure that multi-link communication remains reliable.